Hello, welcome to another Arthur Does Math with a very sick, tired, cold, and wet Mr. Arthur, who just came in from a torrential rainstorm and is now sitting in my icebox of a room. So, if by the end of this video I turn into an ice cube, you'll know why. But before we start talking about the polar coordinate system, which is pretty freaking awesome, I am going to take a very common request and start with a brief life lesson. Okay? Let me share some Arthur wisdom here, and it's going to be illustrated because you all know how good of an artist I am. All right. So say this is you. Okay? And you're a happy person with a kind of misformed head, but no one's judging. Alright? And you meet another person with a slightly less misshapen head, but that person is also happy. I'm sorry, this one's special. And you say to this person, you say, I will do something. And the other person says, I will pay you to do that something. There is an implied contract here. The implication is that you will finish the something, not quit when you're tired or cold or soaking wet or just don't feel like it anymore. You agreed. There is an exchange of money and there is a commitment. So, when you commit to doing something, make sure you finish it. Okay? I just came in from dealing with a very frustrating referee who was too cold and too wet to finish reffing the soccer game. So he decided it was time to go home. Never mind that everyone else was wet and cold and dealing with it like, normal human beings. This guy was special, apparently. So, yeah, not only am I cold and wet and sick, I'm also angry. So this could either be a very snarky video or just straight, boring, straight to the point, and we get done with it. So, anyway, remember the implied contract and be normal people, alright? Anyway, that has nothing to do with the polar coordinate system. Although I will try and tie it in. Okay, that's my goal. Anyway, the polar coordinate system is pretty cool. We've talked about in the past the Cartesian plane, which is the x and y's that you know and love and have been graphing forever. We've also recently talked about the imaginary, or the complex plane, sorry, where we have an imaginary axis and a real axis. Okay, and there's another system that we can use. It's called the polar coordinate system. This one is interesting. It's not labeled the same way that others are. We have what's called the polar axis, and that always starts going to the right, as if it were the positive x-axis. Then we have what's called the pole. That's the origin, okay, but in polar we call it the pole because that makes sense. Just call it the pole. And then the coordinates in the polar coordinate system are given as r theta. That's somewhere in this. Oh wait, I found it. There we go. Okay. R theta. Now, you can probably guess r represents a radius, and it is the distance that the point is from the pole, and theta, as you can see down here, is the rotation that you get to get to the point. Okay, so I had an analogy and it just left me. I'll get back to you on Um, and we can rotate in a positive direction, as we've talked about with the unit circle, or a negative direction, going the other way. And yeah, so that's fun. Now, sometimes I'm going to come down. We'll talk about the stuff in the middle, but oftentimes when you do polar coordinates by hand, you will draw little circles. So, like if that's 1, 2, 3, you would draw concentric circles, or decent. Not so decent. Nope, not even close. That's supposed to go there. And third time, sort of. Okay, but ideally, these circles are the same distance apart, so that if I had an angle of, say, pi sixth, okay, this point right here, I would say is 3 comma pi sixth, because I rotated from the polar axis counterclockwise pi sixth, and I went out a distance of 3. So notice that that distance of 3 is a radius of a circle. So anywhere along that third circle would be a distance of 3. So in graphing by hand, that's often how we do it, although when a computer does it, you usually won't see those lines. Now, it is often useful to be able to convert between what we call rectangular coordinates and polar coordinates. Rectangular coordinates, yep, word of the day, coordinates. Rectangular coordinates are where you have a portion that tells you how far to go left or right, and a portion that tells you how far to go up and down, and they'll form a 90-degree angle, and it's rectangular like. Whereas this polar has none of those corners on it. So we want to be able to convert, since we're talking about complex numbers here, we want to be able to convert between a complex number in rectangular form and a complex number in polar form. Okay, so we have already talked about, they say absolute value here, but this is really the modulus that we've talked about before. Okay, polar form is sometimes called the trigonometric form because they are so closely related, and you thought you were done with trig. Boy, weren't you wrong. And it looks like this, so we're going to use some highlighters here. So there's a lot of words here. I recommend you read them, but I'm trying to summarize. So this is our polar form of a complex number. Right there. Okay, and we usually represent it by z equals r times the cosine of theta plus I sine of theta. Now, where that comes from, you probably don't want to know. I have a project on it if you'd like to see it, but I don't recommend it for, yeah, I just don't recommend it. Just trust me there. Also, you'll notice in this that if we distributed the r, we could put it back in terms of a and b, a plus bi, if we let a equal r cosine theta and b equal r sine theta. Because you'll notice that when we distribute the r to the sine, I get r sine times I, and normally b is being multiplied by I. Okay, when you have your complex number a plus bi. So they're all related, and it's not too hard to convert between them. And r is the modulus, okay, that's the distance you are from the pole. And then there's another word, they call it the argument. Instead of the angle, it's often called the argument of a complex number. That literally means the angle that you rotate through in polar form. And they like to talk about vectors, which we don't talk much about. So there is something that I want to cross out, though, because I don't like it. The angle theta can be found using theta equals tangent inverse of b over a. There is a problem with that. Okay? It is not always true. Alright? A better way to write this, and I want you to write this down, please, is that tangent of theta equals b divided by a. Now, why would I say tangent of theta, and how is that any different? Because don't you think, well, if I just take the tangent inverse of both sides, then I get theta by itself, and I've solved for it. Yes, except remember that whole fun shindig thing we did with how the tangent has a restricted domain and range, and it only gives you values between negative pi halves and pi halves? Well, what if I have a different angle? Alright, what if I want to know on the polar axis where this thing is out here? Okay, what is that theta? Well, tangent inverse isn't going to give me anything in that range. Now, there's ways that we work around it and we use some logic, but I do not want us to put our blind faith in taking the tangent inverse every time. Okay, there are times where the unit circle is a more helpful tool because we could find it over here. Or we'll do a couple other tricks. Let's take a minute to do a quick reminder of the unit circle. You should do that. You should pull it out, look at it, reminisce about all the fun times you had with it, and welcome it back to your life for the next few weeks as we do polar. Yay! I'm not going to pull it out though. You have it. You can get it. So, that's kind of what polar is, and hidden in all this garbledy-goop wordage is the key to converting, and that's really all the assignment is today. All we're working on is converting between complex numbers in rectangular form to complex numbers in polar form. Okay, a couple other things I need to highlight. Color change. All right, this is important. That's important. R is the modulus, so we're going to say R is the modulus. But we know what that is. That's up here. So that makes that important. And this little guy I wrote over here is important. Now, another teacher made this. I have nothing against those that say this, but in my personal opinion, we should just stick with this and solve from there. Anyway, let's do some solving. Well, bam. Look at that. So, convert the complex numbers in rectangular form to polar form with theta on the interval 0 to 2 pi. So, you already know the whole property of periodicity with the unit circle. There are an infinite number of angles, technically, that would put you at the same point, given that you walk the same distance. So, we're restricting ourselves just from 0 to 2 pi. Okay? So, the things that we need for polar form are, as a reminder, so many colors to choose from. Polar form is z is equal to r times the cosine of theta plus I sine of theta. So, we need to find r and we need to find theta. Okay? Well, r is just the modulus. So, no, it's dead. Sadness. Oh, that's a P, not an R. Alright. We'll just let that stay there for a minute. So, R is the same thing as the modulus of your complex number, which we know to be the square root of a squared, so -1, plus square root of 3 squared. How convenient. It's like we planned that. Alright, so all of this equals the square root of 1 plus 3, square root of 4, equals 2. Now, notice that this is a distance, so it makes sense that it's positive. We don't really need the modulus to be negative. If we want to go in a negative direction, we'll change the angle, not the modulus. Okay, so it makes sense that the modulus is 2. And then theta, we're going to... I really did not bury that pen in a very good spot. We put it right. You can't even see that. Never mind. The body was exhumed. Moving on. Theta is, we want to say that the tangent of theta equals b, which is the square root of 3 over a, negative 1. Now, you can also think of this like tangent was y over x. Remember, the b part of the complex number tells us how far to move vertically along the imaginary axis, and the real part tells us left and right. So that corresponds with x and y. So this is convenient. This is the tangent of theta equals the square root of 3, which just so happens to be an angle on the unit circle. Bam. So, I've got one up here at pi thirds, and I also have one over here at 4 pi thirds. So, how do I know which one it is? Well, you got to use a little bit of logic. Okay, think about where this point is on the complex plane. It's worth it to just draw it here. So that's your imaginary plane, that's your real plane. So negative 1 is going to move me to the left, and square root of 3, oh, I see what it did there. Okay, is going to move me up. So I am somewhere here in the second quadrant, which I neglected to remember that there is a negative here. So this is actually the negative square root of 3. So I want the tangent value, or I want the angle in the second quadrant that has the tangent value I'm looking for. So notice that right here, tangent is equal to negative root 3 when the angle is 2 pi thirds. So that's the theta I want. Theta equals 2 pi over 3. Okay, based on this. And again, the reason I chose that one instead of 5 pi thirds is that when I graph the complex point, come down here, the complex number in rectangular form on the complex plane, it's in the second quadrant. And I can't magically move the points around. I want the same point, just in a different form. Okay? I just had a joke and decided it was probably not appropriate, so never mind. Alright, so your final answer after all this fun stuff, I'm really sad that I don't have a red pen. It's just throwing off the balance of the paper. Red marker time. Is that z is equal to 2 times the cosine of 2 pi thirds plus I sine, no, 2 pi thirds. That's terrible. I'm sorry. That's my answer. Okay, they go really fast. Let's do the next one a lot faster. So, let's go. So the next one is 3 minus 4i. So a good just sanity check here is I'm going to move right 3 and down 4. So I'm going to have some point here in the fourth quadrant. Okay, so r is equal to the square root of a squared, so that's 3 squared, plus negative 4 squared. So r is equal to the square root of 9 plus 16, which means r is equal to the square root of 25. So r is equal to 5. Alright, next thing, I want the tangent of theta to equal negative 4 over 3. Now, that's a problem. Problem with that is that's not on the unit circle. So, we do have to go to the calculator here. And we do have to employ the tangent inverse. Okay? So, I am going to say that theta is equal to the tangent inverse of negative 4 thirds. Make sure you're in radian mode. Alright? I know for the last unit we had to go back to degrees. So, hit the mode button. Come down here to radian. So, second tangent inverse of negative 4 divided by 3. And it gives me that, negative 9, or 0.927295218, blah, blah, blah. That's in radians, okay, so remember there are 2 pi radians in a full circle, and pi radians in half a circle, which is about 3. It doesn't necessarily matter so much. Well, it does matter where it is. Negative 0.927 radians. Got to think about where that's going to be. Well, obviously it's negative, so I'm going to be rotating in a clockwise direction. So we'll come over here. I'm going to be going this way. Now, just as a rule of thumb, remember, half a circle is about 3 radians, a full circle is about 6 radians. Okay? So, if I were to divide this into thirds, so like, I should have dotted that. That's off, but get the idea. 1, 2 in here, and 3. Okay, going backwards, of course, because it's negative. You can hopefully get the idea that 1 radian is going to end up somewhere here in the 4th quadrant. Okay, which is where I want it to be. You can trust that the calculator found the right number. I say that hesitantly. Like, the value is okay. You just got to make sure it put it in the right place. Alright, we might have to do some reflecting if it's not there. But this one is. So I am going to say that theta is equal to negative 0.927. And good luck. I mean, if you want to try and get that into a fraction, I don't think it's going to go. Yeah, definitely not. So we just got to stick with that. Alright, it's the best we can do. So my final answer is that z is equal to 5 times the cosine of negative 0.927 plus I sine of negative 0.927. Not the prettiest thing in the world, but it's what we had to do. So just as a guideline, you check your unit circle first. Alright, if you can't find a value for the tangent of theta on the unit circle, then you must go to the calculator. But you've got to make sure that it's in the right quadrant. Okay, we don't have an example on here, and I'm afraid that one's going to come up on the homework. So I'm going to mention something that might not make sense without an example. But remember that there are tangent values that are on opposite sides of the unit circle from each other, and they're the same. Okay, they're separated by a rotation of pi degrees. Okay, so let's say, for example, that I really wanted to find an angle in the 3rd quadrant with a tangent value of root 3 over 3. I want this. Well, I'd be able to find that in the unit circle. Let's say I had a tangent and it was supposed to be over here. Okay, it's not a nice tangent value. Well, when you type it in the calculator, it is going to give you the tangent value on the opposite side of the circle. So how do I get from here to the quadrant that I actually want? Well, you add pi. Okay, I need to go a half rotation around the circle to get there. They're always exact opposites. So I can just add pi. If the number I get doesn't come up in the right quadrant, adding pi to it is going to get you to the right quadrant. Okay. Likewise, I get maybe a negative. I wanted it up here, but it gave me it down here, so I come around, I add pi to it. If you come across those, please try. All right, see what you can figure out, and we can talk about them more later. So, let's. Any questions? Didn't think so. Let's do the second example. Going from complex to rectangular. This is super easy. It's actually very satisfying for some reason. All you're going to do is distribute and evaluate. No, other way. Evaluate, then distribute. Okay, so step 1, evaluate. Step 2, distribute. So what I mean by that is, let's say cosine of 5 pi 6th. What is that? Well, look at your unit circle. Okay, 5 pi over 6 is right here. The cosine is the x value, so that's negative root 3 over 2. So this is negative root 3 over 2, still multiplying by 4, plus, what's the sine of 5 pi over 6? They're always going to be the same angle, so you're going to look in the same place, and that's going to be 1/2. And I'm just used to putting the I second, so we'll do that. And then distribute. Okay, I'm going to multiply them by 4. So I get negative 4 root 3 over 2. Keep in mind, this is like 4 over 1. Multiply straight across with the fractions. Plus 4 over 2i. And then simplify your fractions. We can divide the 4, so I get negative 2 root 3 plus 2i. I guess equals z. And that is it. I don't know, that's fun. It's fun math. Like, it goes from this gnarly looking thing to something, you know, nice and non-threatening. Alright, let's do it again, because it's fun. Cosine of pi over 2, that's the angle going straight up, so that's actually 0, so that was a waste of writing, but whatever. Plus, the sine of pi over 2 is 1, so that's 1i, all times 3. Distribute away, so that doesn't come to anything, 3 times 0, and I'm just left with 3i. Like, that's even better. Like, that was satisfying, but that's really satisfying. And that's really all there is to it. Like, I know this stuff at the beginning can be a little bit confusing. It's a new system. Read over this. I recommend you read it word for word and see if it makes any more sense. But your assignment is just converting between the two. My only caution is make sure you don't have blind faith in your calculator, that you check that the angle that was given to you is in the right quadrant. I feel like I should review that one more time. Unit egg, right there. Unit circle is out sick. The unit egg is taken over. So, remember, this is pi radians. Okay, going half a circle, which is approximately, I put that on the wrong side. Pi is approximately 3. Like, you would never, ever, other than this situation, use 3 as an approximation for pi, but today we are. Okay, so I can make this just rough estimate that those are my thirds. Okay, so if I get something that is bigger than 2 radians when I type it in my calculator, you know, 2.567, I know it's got to be here in the second quadrant. All right, if I get something less than 1 radian, I know it's got to be here in the first quadrant. When it gets tricky is when it's between 1 and 2 radians, and you have to use your best judgment. Okay, but I can guarantee you that when you graph your polar coordinate, a plus b I, that if it's down here, and you know it's down here, you know the tangent inverse is not going to give you a value in that quadrant. It is going to give you a value that is exactly opposite that. So you can use what you know, and then your tangent angle will come up out here when you do tangent inverse. I don't know if that makes any sense. Theta from tan inverse. Okay, and then you want actual. Oh, wow. Pretend you didn't hear that. Actual theta. So again, I'd add pi. All right, it gives me something out here. I'd add pi. That'd give me the angle that I wanted. Going on with my picture. Remember, this is 2 pi going all the way around, which is a very bad approximation to 6. I don't know, but you get the idea. Okay, between 3 and 4, you're for sure in the third quadrant. Between 5 and 6, you're for sure in the fourth quadrant. Between 4 and 5, things get interesting. Okay, and you try and reason it out and maybe use this. Okay, so do your best in the assignment. Go forth and conquer. It's really easy. It's really pretty short. Hopefully you get it done in the time allotted. I could probably keep talking and make this longer than a half an hour. It might even be longer than a half an hour right now, but I am out of energy and I am frozen. And oh, wait, time out. I wanted to relate polar to that stupid ref that I'm still mad about. I figured it out. Okay. Here is our field. Box, arc, box, arc. Feel free to turn this video off by now if you're really just sick of listening to me, but I'm just going to keep rambling. All right. Over here, this is our bench over here. There was another ref. He was pretty chill, and he was actually doing his job and wearing a yellow shirt like he was supposed to. Then there was the ref on the other side of the field who decided that he was too good for yellow because, you know, heaven forbid we put the yellow on the outside, so he wore a black coat like all the other people on the sidelines. And if we consider his position to be the pole, okay, and here's my polar axis right here, we could figure out in polar coordinates the path that he took to go to his car before he was supposed to. He probably did this, so he came around and he went this way. So there's theta, and then he just went to his car, and that would be r. And when he arrived at his car, we could tell him where he is in polar coordinates based on where he should have been. Standing there, reffing a soccer game, being miserable like the rest of us, but doing his job. So, moral of the story, polar coordinates teach you to do your job. That is the thought that I'm going to leave you with. Have fun with the assignment. I will see you guys next time.